been, holy moly, there it has been awful. All right.
Thank you again.
You have a quiz this weekend. The quiz opens today. I think it already did open today, actually. It will be open through Sunday at 11:59. Bring down later. Okay, bring it down later. Thank you. At 11:59 on Sunday, you can no longer access the quiz. Here's the deal. Once you start it, you better be game faced, man. Okay? If storms are blowing through tomorrow and it is, yes, doomsday, not the right time to start that quiz. Because if you start it, your power goes out, you lose your opportunity. Make sure that you have 20 minutes to sit down and take that quiz. You get one shot at taking it, and that's it. You also need to have Respondus Lockdown Browser. You will be prompted to install it through iCollege if you do not already have it. Anyone who was in my class last semester, you should already have this. This is old news to you guys, okay? The quiz was written by me and Dr. Connors. Yes, it opens up today. It is available through Sunday when? 11:59 p.m. because when I used midnight, people told me they got confused and thought it meant noon the next day. So 11:59 p.m. is pretty solid. We should all know when that is, okay? You do not have to start it today. You do not have to start it tomorrow. I recommend you start it before, yes, 11:40 on Sunday evening, okay? I can see when you log in to take it. I can see whether you get kicked out of it or not. I can see the IP address of the computer that you use. I bring this up because last semester I had 3 quizzes turned in at the same IP address within 30 minutes of each other. So before you pay someone to take your quiz for you, be mindful. I will know that you did it. Are we all 100% clear?
Yeah.
Are we all 100% clear?
Yes.
Who takes your quiz? If I find quizzes taken on the same IP address, and I cannot trace that IP address back to the library computers or a school computer, you will get a 0. All of you on the same IP address. Unless you can prove to me that you live in the same house, or there's a really good damn reason that you should all be using the same computer. Are we clear?
Yes.
Are we clear?
Yes.
Okay? Done. And on we go. We finished with, yes. Today. It was on the folder. All of my homeworks get posted with the due date on the folder. The due date was Friday today. Every homework I put up will have a due. I accept all homeworks late. There will be penalties, but I will accept them late at any given point in time because I want you doing it because it's good practice. Okay. We ended with reduction last time of carbonyls. This is how we make alcohols from things like aldehydes and ketones. We have 2 main reagents that we use for these reductions. Lithium aluminum hydride, which I consider a strong reducing agent for carbonyls, and sodium borohydride. And we mentioned that you had already seen sodium borohydride before because it is the second step of your oxymercuration. Yes? Okay? All sodium borohydride is a milder reducing agent. The story I was going to start when I was informed that I ran over class time again. Yes, by the way, someone here in the front, man, wave me the hell down. Yes? We don't like you. Stop talking. Yes? Okay? Sodium borohydride is less reactive. So why do we have both? And it really comes down to storage issues. Okay? The more reactive a reagent is, the harder it is to store for long periods of time. Also, lithium aluminum hydride is a little more expensive than the sodium. But I told you not to focus on cost, focused on application. Okay? The more reactive the hydride reagent is, the less stable it is, the harder it is to store for long periods of time. Okay? It is also more dangerous. Lithium aluminum hydride is more prone to small fires or small explosions than sodium borohydride. Okay? And so, we keep this because for a reasonable amount of the things that we need to do, sodium borohydride is fine. Then we can store much smaller amounts of the lithium aluminum hydride And yes, we have less problems with storage issues. Okay? How many people did their 12-12 lab here? How many of you remember having to weigh crucibles 7 billion times and put them into... See, some people just throw up in their mouth, right? They're like, oh, God. Yeah, I remember. Okay, you remember putting it in a desiccator to dry. What is a desiccator? It is just a closed container that has a material that absorbs water. Okay? That is where we store hydride reagents. We put them in a sealed container with the same material that was in the bottom of your desiccator. It's called Dry-Rite. Okay? It's just a water-absorbent material. Okay? It absorbs the water. That way, your reagents do not. Because even if your lithium aluminum hydride is slowly absorbing water and it's not enough to start a fire or an explosion, it's still slowly starting to degrade that compound and make it non-reactive. Which means if you leave it out in the open, even if it doesn't catch fire, after a few months you go back to use it and you find out your reaction doesn't do anything at all. And that's because what's happened is you've slowly destroyed that reagent over time by letting water get into it. Okay? Yes?
Is that the stuff that people put in their basement to keep it from getting so like this?
Similar. Some of those absorbent materials are very, very much the same. What I was actually going to say is, anybody ever bought like one of these things that's supposed to absorb the moisture from a sealed bathroom with no fan, and then you like plug it in the wall to reactivate it so it's like good for a while, and you plug it in, it warms up and it evaporates all the water? Yeah, those things are crap, by the way. You're trying to absorb a large amount of water into something that absorbs very small amounts of water and then gets saturated. Okay, that is not the way to keep your bathroom dry. All right, but there are different kinds of the same stuff, but it's basically just a compound that you can evaporate the moisture off of, the water off of, by heating, so the water will leave, and then as you let it sit, it starts to absorb it more.
No, it's like little comfy material. It's like
It's exactly right. It looks like little chunks of cat litter, almost. Yes, that's exactly right. But it's still the same thing. It is just, and really most of the time they're forms of anhydrous salts, right? So anybody remember copper sulfate? If you heat it, it goes from blue to gray, but if you leave it out on the counter, it starts to absorb atmospheric moisture and it turns blue again. Exact same process, okay? Are we good with these examples here, I hope? We reduce aldehydes down to primary alcohols. We reduce ketones down to secondary. Okay, these hydride reagents will not reduce other functional groups. They are specific to carbonyls and carbonyls only. And so if I have a compound like this, where I have an alkene and I have a carbonyl, that sodium borohydride is only going to reduce my ketone. It is not going to touch that double bond at all. And so the resulting compound that I get here will be this. That is highly, highly useful because this gives us selectivity. That means that if I know that I need an alcohol but I don't want to mess up my double bond, I have the ability to do that. Now what do we know about double bonds? How do we reduce those? No, mumbling is not how we do it. H2 and a catalyst. Either palladium on carbon or platinum oxide. And we learned when we learned that it is specific just to alkenes. It does not touch carbonyls. So I now also have a method of reducing just the double bond and leaving the carbonyl alone. Okay? This is very, very beneficial when we want to do one thing and not destroy everything in the compound. Okay? So we can selectively reduce this to the alcohol, leaving the double bond intact, or we can selectively reduce the double bond, leaving us with the carbonyl. Okay? What is the next one going to do? So we know that we are going to reduce that. Yes, and I'm going to get 2 alcohols. What about the double bond? No touch. We do not touch the double bond. It will be completely fine. So you'll end up with this unsaturated alcohol plus a molecule of ethanol. Everybody with me on that? Okay, last reaction. What does it do? Nothing at all. Absolutely no reaction. Why? Sodium borohydride is not strong enough to reduce esters or carboxylic acids. This is going to do nothing at all, which we indicate with no reaction. Last semester we learned how to make Grignard reagents. We learned this during the alkyl halide chapter. And then I told you I was going to give you a few uses for it because your book introduces them and then does nothing with them for several chapters. Okay? The uses I gave you for Grignard reagents was, well, one, we know that they're super strong nucleophiles, therefore they're also super strong bases. Which means if we put a Grignard reagent in the presence of water, that Grignard reagent deprotonates water and it gets destroyed. Okay? But what we're going to finally learn now is that there are uses for these Grignard reagents. Okay? Anybody know the name of that aldehyde? Formaldehyde. This is the simplest aldehyde there is. The carbon of the carbonyl is attached to two other hydrogens, and that's it. This is called formaldehyde. If I couple this Grignard reagent with formaldehyde, I will end up with a primary alcohol. Now, I will show you the mechanism once now, but you will not be responsible for this mechanism until we get to the carbonyl chapter. So I will show you the mechanism so that you understand how this works, but you will not be responsible for the mechanism until you see it again during the aldehyde and ketone chapter later on. Okay? So if we have a Grignard reagent like this, first of all, does anybody remember how we make these? What do I make that from? I already spoiled it. I told you what chapter this was in. The alkyl halide chapter. We make these from the corresponding alkyl halides. And we make them by mixing the alkyl halide with magnesium metal in a dry solvent. What do I mean by dry solvent? We did this, I promise. In a dry solvent. What does dry mean? No water. Why? I just told you, Grignard reagents are strong bases and they will deprotonate water and destroy your Grignard reagent. If you have water in here, then it's going to die as soon as you make it. You will make it, that Grignard reagent will react with the water in your solvent, destroy itself, and you will have wasted a whole lot of time and a whole lot of reagent. So we need to make sure that we have dry solvent. The most common dry solvent used for this reaction is diethyl ether. You'll learn the structure of this in a few weeks. Okay? Take the alkyl halide, react it with the magnesium solid. The magnesium substitutes itself in between the carbon and the bromine. Why do we do this? What is the polarity of my bond here? Which one's partially negative, which one's partially positive? What about here? It's reversed. This is negative, the magnesium is now positive. We have inverted the polarity of that carbon bond. We have taken that bond and made carbon, rather than being the partially positive species of that bond, it is now the partial negative. The Germans call it Umbrung, right? It is reversal of, yes, the situation. Okay, question? Can I write larger? Yes, a little bit. Yeah, I can. Are we good with the polarity of those bonds?
Yeah.
What that means is, if we react this bond here and it breaks heterolytically, those electrons belong to bromine, not to carbon. Yes?
Yeah.
But in this situation, if this bond breaks heterolytically, those electrons belong to carbon, not magnesium. Okay? And so what we do is when we mix this now with our formaldehyde, this is our polar bond. That bond will function as a nucleophilic set of electrons. It will attack the electrophilic set here. This set attacks there, forcing those electrons out. That is what forms the bond between this carbon here and this carbon here, which would be this carbon here and that carbon there. This set of electrons, which we said belongs to carbon, attacks this carbon, forcing the electrons up onto oxygen, and what we end up with is a magnesium salt and the deprotonated form of the alcohol in question. What you will see as the second step of all of these Grignard reagents is the same thing that we saw as the second step for all reductions. And that is what? A water rinse. And that water rinse serves one main purpose. Put the hydrogen back on this oxygen. Does that make sense? And so when you rinse this with water, you end up with your alcohol. We can react these Grignard reagents with any carbonyl species that we want. So if I reacted this Grignard reagent with formaldehyde, what kind of alcohol did I get as a product? Primary. All right, let's change formaldehyde into just acetaldehyde. Add one carbon to one side. We'll use the same Grignard reagent. So with the standard aldehyde instead of formaldehyde, what kind of alcohol did I get? Secondary. And that is because when I attack this carbon, one of these is a hydrogen, but the other is a carbon, which leads this to be a secondary alcohol. So what am I going to get if I react that same Grignard reagent with a ketone? A tertiary alcohol. Okay? So if I do the exact same reaction, but I turn this into, instead of an aldehyde, if I turn it into this ketone, which is what? What's the name? Man, we lost it all, huh? Acetone. What's in all of the bottles in that lab that you guys use like water? Yeah? You use ethanol now in Orgo 2. Use it. You're right. Why do you use ethanol to clean in that lab instead of acetone? Because you are doing reactions with ketones, and acetone is a ketone. So if you clean with acetone, your reagent will react with the acetone, not with the ketone that you're supposed to be using. So there is a reason that you use ethanol instead of acetone for the second semester. So what do I get here? Tertiary alcohol. So let's run through this one more time. If I react a Grignard reagent with formaldehyde, what do I get? A primary alcohol. Okay, if I react a Grignard reagent with a standard aldehyde other than formaldehyde, what do I get? Secondary alcohol. And Grignard reagents with ketones give me tertiary alcohols. Yes?
You still do the H2 over it?
Yes, absolutely. Every single one of these needs that water rinse at the end. Really, again, what that is doing is putting the hydrogen back on the oxygen after you've done the first step. Am I doing better on the size of the drawings now? Was that a no? Can we do them? Go. Do you agree with my first one? Yes or no? Propanol. All you're doing is adding one carbon. That one added carbon is now what is connected to your alcohol. There is the carbon you were adding there. You do not have to indicate the magnesium salt residue. We're not interested in the salts. Those are going to wash out in your water rinse anyway. What about the next one? Is that what we got? Carbon 1, carbon 2, carbon 3. Do we agree? Those will attack that carbon there. Yes? There is that carbon there. Again, the carbonyl connected to that carbon becomes the alcohol. This is carbon 1, carbon 2, and carbon 3. Okay. Last one. Carbon 1, carbon 2, carbon 3 attacks this carbon. I'm going to need you guys to turn those off when you show up. Carbon 1, carbon 2, whoops, other way around. Carbon 1, carbon 2, carbon 3, there's the carbon that you carbon. I'm reacting this reagent with formaldehyde. What kind of alcohol did I get? Primary. I'm reacting this Grignard reagent with a ketone. What kind of alcohol did I get? Grignard reagent with a standard aldehyde gave me secondary. Little practice, and you'll be back on this. Count, label, carbons. Keep track of everything. If you don't, you're going to draw something either missing a carbon or you're going to get confused and things aren't going to connect the correct way. Numbering your structures and keeping track of where your atoms are is super important in these carbon-carbon coupling reactions. Okay? There are a considerable number of limitations to this chemistry. Someone give me the first one. I've already given it to you 3 times. You can't have water anywhere near this, man, or it is going absolutely to crap immediately. Really, the number one limitation is Grignard reagents react with everything, man. They react with water. They react with aldehydes. They react with ketones. They react with nitriles. They react with alcohols. They react with amines. They react with carboxylic acids. They react with esters. They react with acid anhydrides. Have I missed any functional groups? They react with thiols. They don't react very much with ethers or sulfides, but that is about it. They are super highly reactive, which means if I have any of those molecules around, or if my compound has more than one functional group in it, this chemistry is not going to work. Okay? So the first thing is they react with everything. And they react pretty much the same way. As a strong base. Now obviously in the presence of something that will not behave as an acid, they behave as nucleophiles. But my students should already know, nucleophiles and bases are the same thing. What is the definition of a base? Lewis definition of a base. Electron donor. What is the definition of a nucleophile? An electron donor. They are the exact same thing. We call them bases when they attack hydrogen. We call them nucleophiles when they attack everything else. Okay? If I react this with water, can water be an acid? So what is my Grignard reagent going to be? This set of electrons will attack the hydrogen, kick that off, and what you will end up with is ethane. Why ethane? Because this set of electrons that belongs to this carbon picked up a hydrogen. What was already on that carbon? 2 other hydrogens. So you will destroy your Grignard reagent and you will create a hydrocarbon. If your Grignard reagent is small, your hydrocarbon will be a gas. And off it goes. Congratulations, global warming just got a little worse. Right? Good job. All you're going to do, yes, is deplete the ozone layer. That's all you're doing, right? You're going to release some ethane, or you're going to release some propane, or you're going to release some butane. Yes? That's all you're going to do if you react these with water. What about an alcohol? So what if I am trying to do, and let me move over here. So last one, then we're going to move on. My question is, if I take this Grignard and I try and react it with, let's say, this. One equivalent to one equivalent. Am I going to add to that carbonyl? What is more likely to happen? Remove a hydrogen or attack a carbon? Always remove a hydrogen. What is going to happen here is rather than my Grignard reagent attacking my carbonyl, there's this really nice hydrogen right here. This Grignard reagent will attack that hydrogen, push those electrons onto my oxygen. What I will end up with is propane and the deprotonated form of my alcohol. The carbonyl won't get touched at all. That's what I mean by the fact that it doesn't have to be an extra molecule in your reaction to stop these Grignards from working. If I have more than one reactive functionality on a molecule, the Grignard reagent is going to react with the most likely one or the most reactive one. Losing a hydrogen is always more favorable than attacking the carbon. Always. If there is something that will behave as an acid, your Grignard reagent will behave as a base before it will behave as a nucleophile. Every time. Are we okay with that?
Yeah.
All right. So by everything, we mean water. We mean alcohols. We mean thiols. We mean any amine with hydrogens on the nitrogen. We mean any carboxylic acid. We mean any nitride. We mean any nitro group. Sulfate group. Got alcohol, I've got thiol, I've got amine, what am I missing? Any acid anhydride. Any ketone or aldehyde or ester or, do I need to keep doing this? Amides. They react with frickin' everything. which means if you only have one of these functional groups in your molecule, you're in good shape. But if I have 3 of these functional groups on a single molecule and I mix a Grignard reagent in, I have no idea what I'm going to get. Because that Grignard reagent is going to react with all of them. It's going to give me a cluster. It's going to give me a nightmare of a mixture of stuff. They're all going to be organic liquids. How do we separate those again? Time to open your mouth again. Fractional distillation. You make yep, see, everybody's real. You make 15 compounds and they're all clear organic liquids. You have to separate those from each other. The way that we separate organic liquids from each other is fractional distillation. All right? You've been warned. That is it for making alcohols. I say that like that was only like 5 reactions, right? Please be mindful of, only the last few of those were new things. Yes? All the way up to reduction of carbonyls, we've already done that. Okay? So now let's talk about what we can do with alcohols. Yes?
Is that the only limitation?
That is the biggest limitation. We really don't need any more. Right? The fact that they react with everything is a big enough limitation. Yeah. What am I doing? What's the reaction? I will accept 2 answers. Substitution or halogenation. They're technically the same thing. These are ways of turning tertiary alcohols into alkyl halides. If I use HBr, this will become the bromine. If I use HCl, the chlorine. Both of these go through an SN1 mechanistic pathway. These will go with good yield. They will go with good yield because unlike some of our SN1E1, once you have created your carbocation, the bromine and the chlorine are good nucleophiles in the presence of carbocations. So you will get exclusively substitution with very little elimination. And that is because bromine and chlorine are very poor bases, but they tend to be reasonably good nucleophiles. So once you form that carbocation, the bromine and the chlorine will directly attack the carbocation, not remove a hydrogen from the framework. So we don't get E1, we will get SN1 only. All of you who took Orgo 1 have done this. It is one of the reactions that you do during the course of that semester. Okay? It is also one of the chemical tests that you use to determine whether or not you have a primary, a secondary, or a tertiary alcohol. If this is SN1, what are my limitations? All right, let me take it one step further and help you out. What happens if instead of one of those alcohols, I try and take butanol and do that reaction? Butanol. What do I get? Nothing. Absolute. I get a mixture of butanol and HBr. Why? SN1 means what? Stepwise, and it goes through what? Carbocation intermediate. What types of carbons do carbocations not form on? Primary. This will do nothing because you cannot form a primary carbocation. This reaction will not work. it will not work because the mechanism of this is SN1. Okay? So what does that mean about the yield on a secondary alcohol compared to a tertiary? Which one's going to have a better yield, tertiary or secondary? Why? One answer. More stable carbocation, period, done. Tertiary carbocations are more stable than secondary. That means you will get a higher yield and a faster reaction from a tertiary than you will from a secondary. And we will get absolutely no reaction from a... So how do I do the primary? Anybody remember? PBr3 is 1. That gives me what? Bromine or chlorine? It's PBr3, yes? Come on, guys. It was not a trick question. PBr3 is a specialized reagent that gives me bromination, yes, of the primary. This works because it goes through an SN2. So what does that mean about this one? What happens if instead of this, I try and use PBr3? Actually, it's not no reaction entirely. I could do what? An E2 elimination instead of an SN2 substitution. In this case, your PBr is not strong enough to do E2, so you just get no reaction at all. Why? What is this again? Do tertiaries do SN2 substitution? Why? Steric crowding of that tertiary center. We cannot do, yes, the PBr3 on the tertiary. We cannot do the HBr on the primary. That is why we have two sets of reagents. If I have a tertiary alcohol, I will use HBr. If I have a primary alcohol, I will use PBr3. If I have a secondary alcohol, for you guys, it's either or. How do I decide which one I'm going to use? I'm going to do small scale reactions of both, and I'm going to look at my yield. Whichever one gives me the better yield is the technique that I'm going to use on that secondary. And here's the deal. Not all secondaries favor the same thing. For some secondaries, the HBr works better than the PBr3. For some secondaries, the PBr3 works better than the HBr. On paper, they both work equally well, right? So you use whichever one you can remember on the secondary. But when it comes to the primary, we can only use what? And when it comes to the tertiary, we can only use the acid-based reagent. The tertiaries will only go through the SN1 mechanism. The primaries will only go through the SN2 mechanism. Are we mildly okay with that, yes or no?
Yes.
All right, does anybody remember how I turned the primary into the chloride? What reagent? SOCl2, we call it thionyl chloride. What mechanism does that go through? If it works on a primary, what mechanism is it? It has to be the same. First mechanism. So tight. We'll do this with ethanol. Okay? Anybody remember exactly what thionyl chloride looks like? Sulfur has what kind of bond to the oxygen? Double bond to the oxygen, single bond to each chlorine. Okay? As a general rule, when sulfur is involved in a reaction, it is going to accept electrons from an oxygen 9 times out of 10. So when you start seeing these sulfur-based reagents getting mixed with oxygen-based reagents, 9 times out of 10, a lone pair from oxygen will attack the sulfur. Okay? In this case, this lone pair will attack sulfur. But what's going to happen? Sulfur's going to have too many bonds. So what happens is one of these chlorines gets kicked off. Now you can think of that in one of two ways. The way that I've just drawn it, which is that this attacks sulfur and the chlorine just falls off. Or I can attack the sulfur, electrons go up, electrons come back down and kick the chlorine off. They actually think it's the latter. That's why I pointed out. I'm perfectly fine with this if you think about it as one step. But in reality, what most people think happens is that the pi set goes up onto the oxygen, and then when it comes back down, then it kicks the chlorine back off. Okay? Just so that you've been warned. This takes me to something that looks like this. Generally, this reaction will be run in a basic solvent. Someone pick my favorite basic solvent. Pyridine. My favorite basic solvent is pyridine because it's rock solid. The only thing it ever does is behave as a mild base. But it's a great solvent because it dissolves everything. Pyridine is usually the choice. That will come in and take that hydrogen, put the electrons back on your oxygen. Okay? Can I go over the other board? As in, so what do I have now? Everybody with me? Yes or no? What else do I still have? Now I know that up till now this does not seem like an SN2 because we just did a whole bunch of stuff and none of it was a substitution. Yes? What you have done is you have taken an alcohol which is not a leaving group. You have attached it to this sulfur. That now makes this oxygen a moderate leaving group. Because what's going to happen now is, we know this is partially positive, this is partially negative. My chlorine will attack the partially positive carbon. That will break the carbon-oxygen bond, and that bond will form a double bond between the oxygen and the sulfur, which will kick off the chlorine. And what I will end up with is my chloride, sulfur dioxide, and a molecule of HCl. For those of you who had me last semester when we talked about thionyl chloride, I talked about the dangers of thionyl chloride. One of those is that it is heavily reactive with atmospheric moisture. I even mentioned that when you open bottles of thionyl chloride, especially like in this room right now, where it is warm and the humidity in here has got to be like 8 billion. Yes? The water will react with this, forming sulfur dioxide and HCl vapor. The fumes that you see coming off the bottle of thionyl chloride when you open it is HCl gas. How's that going to go if you inhale it? Really bad. It is a slow and painfully excruciating way to die. You will dissolve your lungs from the inside out. Thionyl chloride is not a joke, and if there are spills of thionyl chloride, do not, under any circumstances, try and clean that spill up. Get out. Get out and notify somebody. Don't be an asshole. Don't just leave. Whoops. Right? Then people are going by, my eyes burn. Why? And then people are getting sick and vomiting in the hallway and no one knows because you're an asshole. Yes? If you spill a bottle or you know a bottle has spilled, notify people. Everyone knows, well, everyone in my classes know I love dangerous chemistry. I really, really do. I only have 5 minutes so I can kill some time, okay? I love dangerous chemistry. It's so much fun to do. There is nothing more exciting to me than watching my heart rate just, oh crap, oh my goodness. But when I do dangerous chemistry, I also make sure that I am using appropriate safety protocols, safety equipment, and proper PPE. What is PPE? Personal protective equipment. Okay? You need to make sure that you understand all of the hazards involved with the things that you're doing. In fact, any student in our department that goes into undergraduate research has to complete training in what we call right to know, which means that you understand that you have the right to know about any and all hazards associated with what you do. But there is a second part of that. You are obligated and personally responsible to find out about those hazards on your own. If you were informed that there are hazards involved in what you're doing, that you should look that up, and you just go, later. You're the one at fault. You injured yourself via negligence. Yes? I bring this up because how many of you are in my Orgo 2 labs right now? Hands. 2 people? Who's doing Orgo 1 lab right now? No one's doing lab. This is an amazing semester for a lot of people, right?
They're all under this one.
How many of you have looked up one compound to see the hazards involved with even one of the compounds in the lab? Good job. Thank you. You should. You really should. All right. Here's the deal. I will not make you know the mechanism for PBR3. It is far more complicated than SOCL2. We will stop here today. I will pick up on, what is it, Wednesday with tosylation. Come on, man. We are not, Monday is a big day. We're not here. Have a good one, guys. I'll see you next week.